Yeah, it's like we can start over here. Good morning, all of you. Yeah, welcome you back to the CAN course on hybrid renewable energy system and microgrids. Today we are at day 3, and today Professor Saad is going to deliver on the power electronics and microgrids. It is a continuation of the last lecture of Professor Saad. Yeah, Professor Saad, good morning.
Good morning.
Good afternoon, sir. Yeah, you can go ahead of sharing your screen, Professor.
Okay, thank you very much. Thank you. Okay, share entire screen. Yeah, that's the thing. Share. So now put it on slide mode show. Okay.
It's fine.
Can you see?
No, go to the display settings.
Can you see the slide?
Yeah, we can see the slide, but go to the display settings and make it the full screen.
I already put the display setting. Yeah. Swap.
Yeah.
Presenter with the slide view, right? Like this.
Yes.
Huh? Can you see now?
Yes, fine.
Okay, I think so. Good morning, everyone. So I think we stopped yesterday somewhere here. Get the pen. So we discussed the PV modules. I think we have discussed this, which is the location, as we said, very important to to select the right locations, because that determines the amount of solar access to the panels. So very important. And then the next one, which is the tilted angle. Okay, and then we said, I think the tilted angle here has multi objectives. It's not only, yes, one of the objective is the main objective is to maximize the amount of solar irradiance absorbed, but it has also another one, which is, for example, the auto cleaning, the cooling, and also the loading effect. So, and these have to be selected. Some of times we have no much choice. For example, if in case of the retrofitted systems. Retrofitted systems means already the roof exists. That means it's been built. So like this, we have very limited, I call freedom, how we are going to fix the tilted angle. But if it is like, for example, a new home, wherever, so the orientation of the home, the tilted angle of the roof actually can be done effectively, So, okay, so I think we have seen this. We have seen the tracking. I think, as mentioned yesterday, tracking is one of the good things, but it involves a lot of mechanical. There's a lot big motors here, and these motors need to move, and they require quite a large amount of power to move, to track the maximum. But this is the ideal case. However, the mechanical part, the moving part, is quite a challenge to achieve. Okay, I think we have the storage. We talk about the storage. I think very important. The selection of the storage, it's very, very important. Maybe let me go back to this card. Show you some the selection. How we select the storage storage systems. Okay, just a minute. Yeah. Yeah. We discussed a bit on the storage, because yeah, this one, yeah. Now let me share, present entire window. Screen one, okay, share.
Hello. Hello. Yeah.
Yes, can you hear me?
Yeah, okay.
Okay, and then present mode. Can you see this? Can you see my slide?
Yes, yes. Go to the display setting, Professor.
Oh yeah, display. How about now?
Yeah, it's fine.
Okay, so one of the criteria on how we select the storage, that's very, very important, because we have different types of devices actually that can be used in storage, So, for example, if you look into this chart here, it shows the power and then the time. And we can see we have different, for example, we have ultra capacitors and supercapacitors, which actually they have a very high power density, but they have a low energy density. The electrochemical batteries, it's one of the best choice actually to be used with renewables and microgrid systems. Okay, and what else? Yeah. So in even in the batteries, in the electrochemical batteries, we have a variety and a wide range of selections of batteries, and the selection of these batteries, for example, depends on the energy density, power density, and then the lifetime or the number of cycles. Okay. So, for example, if you look into lead acid batteries, which is the cheapest in the market, you see they have the energy density is between 20 to 35 watt per kilograms, 25 watt per kilogram, and around between 100 to 2000 cycles lifespan. Look into the lithium ion batteries, it's almost 4 times or more than 4 times the energy density. Okay. And also the number of cycles, yeah, it's relatively high, around 500 to 2000 cycles. Lithium polymer, it's around 200, around 1000, and then greater than 1200. You see, and there is also the nickel cadmiums and other batteries actually which have things. But you can see the last one here, the green one, which is the solid state batteries. Okay, and this can go very high power density and also a large number of cycles. So the selection of these batteries actually plays an important role. And recently, we see the introduction of these ultra capacitors. Okay, as we said before, they have quite a high energy density, which is 1 to 10 compared to capacitors. Okay, but they have very high power density, which is 5 to 20 kilowatt per kilogram. So it's very high. And then the cycles, 500,000 cycles. So which make them quite suitable and useful for some applications which requires fast response. Okay, and also the operating range of temperature, quite good, because as we know, batteries are very sensitive to temperature. So these ultra capacitors actually they can play a role, in especially in cool weathers, and especially in North America, Canada, whatever, Northern Europe, Scandinavian countries, where temperature goes below negative 30, and then also hot plus 60. So this is a good choice. Sometimes we may combine the ultra capacitors with in some of the applications which requires faster response in microgrids. And this is the comparison. This is spiderweb. This comparison of different storage systems, and then how we select them. You can see we have the the 7 parameters, which is mainly the what you call energy density, power density, temperature, operating temperature, cycle, price, price per kilowatt. This is price per kilowatt hour, price per kilowatt. So if you look into the ultracapacitors, the ultracapacitors actually has a very good power density. Yes, they have very low energy density, where it's expected. Okay, and they have they can operate at a very high temperature. Okay, very good. All right, and they can, a lot of cycles, a lot of cycles, and very good. And also price per kilowatt is quite so good. But if you look into, for example, the most commonly used lead acid batteries, lead acid batteries quite safe. Okay, they are price per kilowatt hour is quite cheap, as expected, as we know all. However, it's not very highly rated in terms of, for example, the energy density and the power density, and also the operating temperature. So the lithium ion, so also have very good energy density, So this is the chart that we use to select the best storage system. Okay, because as I mentioned yesterday, when we are building the system, it's not one component. It's not only the photovoltaics. When we have the storage also plays an important role. If the efficiency of the storage systems is no good, then that affects everything. Okay. Also, let me. Yeah, these are some examples. So these are some examples of the intercapacitors available in the market, and in terms of voltage, farad, and energy density and power density. So the integration of this what you call energy storage systems into the systems actually plays a very important role. It's either batteries or ultracapacitors, depends on the application, but it plays a very, very important role. Means, for example, if there is if you're having a system A here, maybe it's a source, it's a photovoltaic, whatever, and then we have the power processor. Okay, and then we have a system B, maybe it's a load or a motor or whatever, and then you have the storage here. So this storage actually will help in case, for example, you can see here the power delivered from the source is quite constant. Okay, however, in the load side, you can see the power fluctuates, goes up and down. So if, for example, if we assume that system A is a diesel generator, okay, or maybe it's so can you imagine can you make the diesel generator match the load? Okay, it's very, very hard, if it keeps from up, down, up, that's not really possible and practical. So what's one of the objective of the energy storage system is to compensate it. So the system A here can provide a constant power. The system B require a variable power, and the difference can be provided by the storage systems. So this is one, because in microgrid systems, most of the time we have batteries, okay, and sometimes we have diesel generator. Okay, if we assume that is isolated system. If we have this kind of systems, so what happened? If the load changes, for example, we have solar, we have diesel generators, and then we have battery systems. Okay, 3 components. For example, if the load keep up and down, so the generator will keep turning on and turning off. But to avoid these kind of issues, we call it, this is called the part load condition. Part load condition. So there's a sudden increase, sudden decrease in the load, which maybe the PV system is not enough. So what happened? The diesel generator, and that's the algorithm that we design, have to play an important role actually, which system have to turn on. So if the load increases, the diesel generator will turn on. So, but what we do actually most of the time, we don't turn on the diesel generator. We supply the power from the storage system. Okay, and once the storage system energy or power drops, then the diesel generator will turn on to charge the batteries. So most of the time, the operation is between the PV and the storage, because the turning on and turning off of diesel generators it leads to a lot of maintenance, because turn on, turn off, turn on, turn off is not good for the diesel generators. And that's why I want to show you some examples. So this is what the role of the storage do. Let me, for example, if we have a load, so this is, for example, in some applications where we're having a motor, for example, a water pump or whatever, So in the microgrid system, so at the starting, you have a very high power demand, and then goes back, because the rating here is around 150 kilowatt. But actually at the beginning, because very high rush current, and that's actually to start, because it's moving from static to dynamic. So, okay, so that's, and then it goes to the rated power. So during this peak here, so there are two options. Either we over design the systems to cater for this, or we provide a storage which can be used. And the same things in the braking. Okay, the braking, there is a lot of energy which can be reutilized. Okay, and this is how, for example, when you have a system with storage, for example, you have the electric grid or whatever, and then we have the inverter, which is the AC to DC. This is a rectifier, and then we have an inverter. This is the VSD, okay, and then connected to the motor, okay. And what happened here? The storage systems here will provide the extra power, and also can be recharged from the braking of this motor. Maybe we take another example for renewables. Okay, for example, one of the common examples, which is the wind energy systems in microgrids. As we know, the wind changes depends on the wind speed, the wind power. Okay. So what happened actually? If you have a system, okay, a wind turbine, okay, you have a wind turbine, okay, and this is the power profile. You can see, and the power profile actually follows the speed profile. So it does fluctuate, because you can see in this formula the power is dependent on the velocity, on the speed. V cube means small change will result in a high change in power. Okay, so there are many ways how to control this. Sometimes we adjust the what you call the angle. Okay, sometimes we do the braking, but sometimes may not be enough. So one of the ways that we usually use is what you call using the storage systems. Okay, and these storage systems, because this will help not only to supply the load, but also to maintain the power that is being injected to the grid. Okay. So this is very commonly used applications. Actually, that's helps. So this is what happened here. So what you can see, the DC bus is always a constant, and you can see the charge and discharge. The charge and discharge depends on the wind speed. Okay. Yeah, I think maybe. Diesel generator. Yeah, this is actually quite important, because this is commonly used in microgrids. So once we have a diesel generator, okay, so these diesel generators usually provide the power. Usually we have rectifiers, and then we supply the load, okay, and then we have dynamic braking to store the energy. So 30 to 40% of consumed fuel is burned to the resistors. Okay, means converted to heat, so 20 to 30%, which is a consumption between 15 to 25 liters, of these types of things. So one of the way is if we incorporate storage. You can see here, when we incorporate storage, Okay, and that actually will help because this one will provide a constant, okay, and then it will supply the fluctuating power from the load side. So this is what happened. Okay, so the capacitors will charge and discharge, and then what happened, we will have a constant what you call supply. Yeah, I think maybe that's all. This is just for what you call for the storage. So let's go back to my presentations.
Sir, I have a question. Can I ask now?
Yeah, please go ahead.
Yeah, sir. You mentioned sir, power density and energy density with respect to the storage devices, especially battery. I'm not very clear, sir. What is difference between power density and energy density? Can you please little bit elaborate on that?
Yes, sure. Okay. Let me put the presentation, entire screen, this one, two. Okay, let's screen share. And then go to the PowerPoint. Okay, let's go, I think this one here. Yeah.
Yes, sir.
Can you see the slide?
I think the previous one, there was one table.
I want to show you the spider chart.
Yeah,
Okay,
that's fine.
Yeah, you can see that. All right. So if you look into this, what you can see? Oh, sorry. Where is the? I was looking for a pencil. Yeah, pencil, pen. Okay. If you look into, for example, like I said just now, the capacitors, the ultra capacitors. Okay, the ultra capacitors, they have a very good power density, but very low energy density. What does means that? What is the energy? Energy is a power times time, right? You agree?
I agree with you.
Okay.
Power into time is energy.
Yeah, energy equal time times power.
Yeah.
So what does this mean? It means they cannot hold a long power for a long time. You know, they have very low because they can charge very fast and discharge very fast, right? You agree?
Yeah, I agree with you.
Okay, so that is the main characteristics of capacitors. They have a very high power density, but not energy density. The opposite for batteries. If you look into, for example, I call lithium ion, for example. You look into lithium ion batteries, okay? Lithium ion batteries, they have a very good energy density, right? But they have very low power density. Okay? So it means they can provide, sorry?
Yeah, clear to me.
Okay, good. So means in some applications we need to combine both. For example, batteries and the ultracapacitors. You know, okay. So the ultracapacitors will give you the fast response, which can charge and discharge very fast. Batteries will provide you the durations. You know, so that's how we select them. Okay, is this clear?
Yeah, it is very clear, sir. Thank you. And I have another question related to the same only, sir. Ultra capacitors. Can you give us some industrial applications, sir? Where exactly you? I remember first day you said it is useful in racing car or something. Apart from that, any other uses, sir?
Yeah. Okay, I can show you here. Okay, let me present, pull the slideshow. I have shown just now an example. I think you may have missed it. Okay, the way swap. So you see here, this is an application. Okay, you see, this is the ultra capacitors. Can you see this slide?
Yes, sir, I can see that.
You see, so this is the ultra capacitors here. Okay, these ultra capacitors actually You see, we have here a DC-DC converter, which is a bidirectional DC-DC converter. Okay, so what happened is, so here, for example, if we assume it is an electric grid or microgrid, whatever, So, and then we have a motor. This motor, maybe it's a pump or maybe a ventilation system in a hospital, whatever, So what happened here? This motor depends on the load, right? Sometimes the load increases, sometimes it decreases. What happened? So that keeps the power keep fluctuating, right? The power will be like this, right? Sometimes up, sometimes down. Sometimes it's goes up and down, right? So that's what happened. So if we have to supply this power profile from the grid, that is, we will first one, we will have to over design the system, so we have to pay a lot of penalties for the excess power. But if we can supply a constant power, and then the remaining part above or lower can be supplied by the ultra capacitors. And then when during a breaking, the energy can flow back to the capacitors to recharge. We call, for example, regenerative braking. And this is also used in electric vehicles, by the way. Regenerative braking. Yeah.
Okay.
Yeah, it's used in electric vehicles. For example, if you assume that you are moving at 100 kilometers per hour, and then suddenly you start braking, so that energy actually goes back and stored back into the storage system.
Oh, pretty clear, sir. Now I'm clear. I have just high level knowing that yes, BFD has some storage devices capacity, but I was not pretty clear how does it work. Now it is very clear to me, sir.
Yeah. As you can
Yeah,
see, the
thank you.
energy storage unit is separate from the VSD. This is the VSD, the variable speed drive, right? The DC,
Yes.
AC to DC, and DC to AC, right? So this is additional components, for the system. All right. Any other questions before we move from the storage? Okay, and slideshow is gone. So let me. Any questions in the chat box? Usually 30 minutes, and then we will have questions. 30 minutes, 30 minutes. So we have 3 sessions of questions.
I have a question.
Yeah, please go ahead.
So when the ultra capacitors are connected all the time with the circuitry, means control circuitry.
Sorry?
Means your power. When the ultra capacitors are connected continuously with your power circuit, don't we consider this as acting as a load also?
It acts as a load and also act as a source in both times. When it is discharging, is acting as a source. When it is charging, is acting as a load. Because
so
when
during
you have
that time, what would be the power factor corrections methodology? Because since it is acting as a capacitor, as a load and then source, probably there may be a changes in the power factors, right?
Yep, that's very true.
So how it must be nullified?
Yeah, and I think that's the job of the VSD. One of the jobs of the VSD is try to maintain a good power factor. Because VSD we have a rectifier, which is actually introduce a lot of harmonics, and then we have the inverter. So through the VSD, we try to control also the power factor. And you may have additional capacitor bank. Okay, especially for large systems, you may have a capacitor bank actually which had to rectify or adjust the power factor.
So means it is a separate power factor unit must be connected with the system.
Yes. Yeah. That should be a separate power factor correction unit. Yep.
Okay.
Okay. All right. Any other questions? Okay. So if not, then we move back to the slides after we discuss the storage. So share entire screen number 2, share. And then put on slide mode show. And then slide mode show. and then display setting, swap. Okay, I hope you can see now the slide, right? Okay, good. So let's go back here into the batteries. I think we have talked about the batteries quite enough. Yes.
Can you go to the display settings and change?
Oh, sorry. Display setting.
Yeah.
Yeah. How about now?
Fine, it's fine.
Okay. So this is after one of another component which we talked yesterday about the inverters. So we have a wide range of inverters. Okay. We mentioned about the starting from a micro inverter, which is around 300 to 500 watt. We have seen string, multi-string, okay, and then we have the central inverters. So we have a wide range of selections. Actually, depends on the power ratings and our objective actually of the design of the microgrids. And these are some pictures. You can see this is a standalone inverter. You can see it's a single phase unit. It's a 600 watt, okay, single unit. This is a furnace inverter, interactive inverter, which is grid connected. Okay, so this sorry, yeah. So this is another inverter here, where you can see the inverter, and also on the bottom there is a storage, the batteries, and all these circuit breakers and the protection from the DC side and the AC side. Okay, so these are some examples. And also, so most of the time when we're having what you call the batteries, we must have what they call the charge controllers. Okay, these charge controllers actually are important to maintain, because one of the things that destroys the batteries is the overcharging and over discharging. Okay, so when you overcharge or over discharge the batteries, actually that's it. So most of the time we will have these charge controllers that can be used, and it have to be rated accordingly, and also they come out with display. So also we have integral inverter charger together built up in one system. So this is one systems built in. Okay, or you can have also separate charger, okay, selection. But as I say, always the selections, we will discuss about these selections of the inverter, how we can select the inverter. So that's the biggest challenge, actually, how to select the biggest inverter. Any idea how do we select inverters for photovoltaic systems? For example, if I have, or maybe we come to this question later after this. Okay. So we sometimes we have a DC-DC converters, which is between the PV and the inverter, and this DC-DC converters actually play a role in terms of regulating the voltage level. Okay, but also it can what you call add on a cost, and also on some of the losses, and the AMI interference. Okay, and there are a number of DC-DC converters that can be used actually in a photovoltaic systems, starting from a buck converter, boost, buck boost, choke, zeta, specific converters. These are non-isolated. Okay, and non-isolated can be used in when we're having a transformer-based systems. Okay, so means you have, for example, like we mentioned yesterday, we have the 50 hertz or the high frequency transformer, and also we can achieve isolations in a DC to DC stage, where we have also a number of DC-DC converters which comes with the high frequency transformers, like the flyback, the forward, the single-ended, and the phase shift full bridge. So there are quite a number of them that can be used. Let me go back to the inverter, actually. The question is, how do we select the inverter? For example, if I have a 1 kilowatt peak PV systems, what will be the rating of the inverter? If I have a 1 kilowatt peak, 1 kilowatt peak PV panel, okay, PV what you call modules connected. It's the total power is 1 kilowatt peak. What will be the size of the inverter in terms of power? Any idea? Or maybe
1.2 times above.
Sorry.
1.2 times above the
One. Maybe stop. Let me end slide. This guy. Maybe in the chat. Anyone in the chat? What will be the size of the inverter if you have 1 kilowatt peak, 1 kilowatt peak PV system? What will be the inverter? Okay, there is one answer here. It's 1.2.
Yeah, it can be definitely more than 1 kilowatt, considering the losses in the system. So we can take some margin, probably 10% or 20%. I'm not very sure, but one thing is sure, definitely it should be more than 1 kilowatt. So 10 to 20% should be okay, as for me.
Means 10 to 20% means 1.1,
1.2 G.
Yeah. Okay. Any other guesses or ideas? Okay. Before answering these questions, you know the inverter has an efficiency curve. Right? The inverter efficiency is not constant, right? Do you know that, right? The inverter does not have a constant efficiency, right? So what does it mean? It means actually the inverter has an operating maximum efficiency. For example, we see 90% efficiency curve. You know, maybe I think I will use the board. This is very important, you know, to what will be the size of the inverter. Okay, present entire screen number 2, share, then put on slide mode show. All right, and then display setting. Okay, I think you can see now, right? Okay, so let me you know, this is more. Can you see Dr. Siva?
Can you go to the display settings, Professor?
Sorry?
Display settings and
display. How about now?
It's fine.
Okay. So in the inverter, let me draw here. The inverter efficiency has what you call an efficiency curve, something like this. You can see this is the efficiency curve, for example, of if we assume this is a 1 kilowatt. Huh? This is 1 kilowatt. This is 1 kilowatt system. So means the inverter has a maximum efficiency at 1 kilowatt, which is this point, right? Means if you have an inverter and you operate this inverter at 500 watt. For example, assume this is 99% efficiency, yeah? 99% efficiency. So if you operate the inverter at 500 watt, you know what is your efficiency? Is half. Okay? So if you operate lower one, for example, 200 watts, so the efficiency will drop. So what does it mean? Means when we select the inverter, we have to make sure that the inverter operates at its maximum power, rated power, at its maximum rated power. For example, if we select a 1 kilowatt inverter, means that inverter should always be operating at 1 kilowatt or close to 1 kilowatt to get the maximum efficiency. But if it's operate lower than that, then we lose on the efficiency. Okay, so now we back to the question. If I have 1 kilowatt peak PV panels, PV systems, what will be the size of the inverter? okay, if taking it by the logic, it says that if 1 kilowatt, we need to have 1 kilowatt, and then we add safety margin of 10 to 20%. Okay, maybe increase, but actually, it is the other way around. If we have a 1 kilowatt peak PV systems, the inverter usually it's an 800 watt. Why? Because when we see 1 kilowatt peak, means actually that peak is only achievable because when we see the data sheet of the PV panels, we have what we have the IMP, VMP, VOC, ISC. Okay, so these are actually done at the lab level. At the real systems, and we include the losses, from the PV panels to the DC-DC converters to the inverters. So actually the inverter should be lower by 20%, not more than 20%. Why? Because we want the inverter to operate at its maximum power, rated power, which is to achieve maximum efficiency. Okay, and later on we have some calculations, and I will show, because we have to do derating. For example, if we have PV panels, okay, so example, and because the data sheet is provided under lab condition, we call it STC, standard test condition. So that data in the data sheet, actually, it is ideal. So when you put it outside, when you put the PV panel outside, so you have a lot of losses. You have losses due to the dirt, losses due to the mismatch of the cells, losses due in a wire, losses due in a converter, losses. So you have a lot of losses actually. So in order for us to make sure that the inverter matches the power produced per minute, we have to derate it by 20 to 30%. Even we can go even to 700 watts. Okay, and we will demonstrate this. We will do some calculations, and I will show you actually how why we have to derate this. Okay. Any questions?
Sir, I understood the concept which you explained. Just one thing.
Yes.
What is the short-term overload capability of the inverters? I do understand. I agree with you, because all might not have peak generation, so it doesn't make any sense economically also to go for the same size, which probably hardly we are using. But let us take a case if some inverters will see the peak peak power from the PV cell, then probably it might be for very short duration. So for that short duration, if we are sizing 20 to 30% low, it has to withstand as well. So can you tell us, sir, a little bit on?
We have the protection. If we have over current or over voltage, they have the protection. So the inverter will be disconnected. Okay. But 99% of time, or 99.99%, the inverter will always operate lower than that. Because as I said, the PV panels, the data sheet is provided under STC. STC, what does it mean? Standard test conditions. Means, under ideal means there is very clear skies, very clear, there is no dust on the panel. The panels are new. The temperature is ambient, is room temperature 25 degrees C, because the measurement of the temperature actually decrease the efficiency of the PV panels. Means, what does mean decrease? Means that will decrease the voltage. Because once the temperature increases, the voltage decreases from the PV panel. You know that. I think we have some slides on the MPPT later. We will show it. So this is what happened. So the 99.9%, the inverter will never exceed the 1 kilowatt or even 800. And let me show you some examples. Okay. And also we have protections. If in case there is overcurrent or over voltage, there is a protection that actually can protect the inverter. Okay.
Okay.
All right. Good. Let's take. This is other different types. Okay. So in the PV panel, okay, the voltage and current that is produced from PV panel depends mainly on two parameters. Okay, one is the irradiance, another one is temperature, right? Okay, these are the two factors. And maybe let me show you, I think the next slide maybe show you. Okay, if you look into this slide, so this is the power curve that is produced from a PV panel. You can see the irradiance changes from 800 watt per meter square to what you call, to 800 to 1000 watt per meter square, and you can see at different we have a different power curve. Okay, the solid line is the power curve. The dashed line is the IV curve. You can see IV curve is current versus voltage. Okay, and then we have the power curve. You know, so the solid line is the power curve, right? And the dashed line are IV curve. So we can see that actually the IV curve does change, depends on the irradiance. Okay, so this is from here. If you look into this dash curve here in the second figure, what you can see, like I mentioned just now, these are under different temperatures. You see 0 degrees C, 25 degrees C, and then 50 degrees C. What you can see? You can see there is a drop in voltage. This is drop in open circuit voltage. So as the temperature increases, okay, as the temperature increases, there is a voltage drop. And when there is a voltage drop, means there is a power drop, because voltage power equal to voltage times current in the DC system, right? Okay, so and there is you can see there is a slight current increase, but if you compare with how much we drop here and increase here, because when the temperature increases, there is a slight short circuit current increases, but not much compared to the drop here. So in the average, the total will be actually the power drops. So we can see the PV panels are very sensitive to irradiance change and temperature change. And that's why I say just now, the PV panels usually are tested under STC, standard test condition. Okay, so the standard test condition is 25 degrees C. Okay, 25 degrees C, but sometimes, most of the time, we operate not 25. Most of the time is either more, especially for hot countries. You know, I think India, South India, for example, can easily reach 50 in summer. Okay, 25 maybe in winter. Okay, so so this is the situations, and that's actually which gives us the how we can select the inverters. But later on we will calculate. I will show you how to calculate things. Okay, let's go back to this. So the solar changes between the relationship between temperature and the irradiance. MPPT is also moves non-linearly, you know. So you can see the power curve here. So we can operate at this point, we can operate at this point, we can operate at this point, but there is only one point, which is the MPP, which is here. And this MPP, okay, this gives you the VMP here and IMP. Okay, so this is what we call the maximum power points. And each IV curve have only one, what you call power point. Okay, so like you can see here, yeah, like here, like you can see if the power curve here, we have like 2 points here. One is possible here, but the ultimate one is here, you know. So it should be somewhere here. So when we do the study, we found actually the MPPT can improve the efficiency by 15 to 20%. Okay, means try to push the system to operate at its maximum power. Okay, and you can save in around 15 to 20% of power. And there are many methods, MPPT methods that can be used. Okay, many MPPT methods, and this is a quite also interesting topic to work on, especially for researchers. And I encourage, because this MPPT actually, the good things about it, it does not require a lot of hardwares. You know, you just need a DC-DC converter, and then that's it. You have a controller. You can use Arduino or any other microchip, whatever, and then you can do the programming. You know, and you can do research with a very low cost. You know, because sometimes when we do research, we have to also care about the facilities available. Since you need a DC-DC, maybe if you have solar simulator, will be good. Okay, but if you have a DC power supply, a DC-DC converter which you can build yourself, actually, which is one switch, one inductor, one capacitor, and that's it. You know, and you can test and you can publish a lot of papers using this kind of low-cost research. Okay, so there are quite a number of methods available in the literature, and we also, our group, have contributed significantly actually to this area. You know, our group consider number one in the world in MPPT. You know, we have done a lot of work on MPPT controls. So we have the fractional open circuit voltage, MPPT, fractional short circuits, intermediate, perturb and observe, incremental conductance, hill climbing. Now we're moving to AI-based methods and so on and so forth. There are quite a number of methods. For example, usually when the irradiance change, so what happened? The power will move, for example, from here to here. So we should be able, when the irradiance changes, the algorithm should be able to track this. And then when the power changes from here, it should be moving here. The same thing happens in the opposite. If the irradiance drop, the algorithm should take you to the next peak, because here this curve is a number of points, so it may take you to the wrong peak. If it drops further, it goes to take you this. The same things when the temperature change. So, but most of the time we test the system based on the irradiance for the MPPT. Okay. All right. There are quite a number of methods, okay, available in the market, but in industry, still the P&O is the most commonly used algorithm. Okay, it's quite because it's quite simple. It doesn't require a lot of computation, and it's very generic. And then there's a constant voltage, there's a constant current also, short circuit pulse, ripple. There are many methods actually. There are hundreds. PSO. Now we have machine learning. We have quite a number actually of methods. So, but the good things about this methods actually, it's to see how this method actually performs during a cloudy day or any clear day, because that's the use. If you have a clear day, actually maybe you may not need it, but if you have a cloudy day, so you may need it, or the cloud is moving. For example, if you look into this curve here, so you can see the red one, which is the theoretical power, and then the black, actually it's overlaps, with this. You can see actually in a cloudy day with the MPPT, we are able to extract the maximum power available during the day, from morning up to the evening. Okay, and you can see all the time it's overlaps. You can see here the algorithms is activated only after a certain amount of power, because maybe the power is too low here. Also, the power drops quite low, so it disconnects. So, but this is, you can see it's clearly it's overlaps with the systems. And you can see here we are able to reach almost a 3 kilowatt power. So in on clear day, you can see there is less oscillations due to the clearance, clear day. And you can see the MPPT actually is able to also to track the maximum power and make sure the system is always operating on a maximum power. You may see here this doesn't change much, but it's quite important. Okay.
Sir, just one quick question. So this MPPT control what you showed, this is inbuilt feature of the inverter. Is my understanding correct?
Sorry.
The MPPT control, maximum power point tracking control mechanism. So this is part of. I mean, where this get it done? If I understand, is this part of the? I mean, is this a job of inverter to do that? MPPT control?
This is an additional DC-DC converter which is located between the PV and the inverter.
Okay, this is not part of inverter.
No.
Okay.
This is an additional hardware.
Additional hardware. Okay.
Additional hardware which is located between the PV panels and the inverter.
So, I mean, being a buyer or a developer who is going to set up, let us say, a plant. So, I mean, what happens? MPPT by default it comes everywhere, or it is a choice of the developer or customer.
It's an additional hardware. It's a choice. Your inverter, you have when you have an inverter, the inverter have what you call operating window voltage. Okay, means the inverter have an operating window. Means, for example, they operate between 150 volt to 600 volts. So, if the voltage that comes from PV panels is within the range of 150 to 600 volt, the inverter will work. If it is dropped below 150, then the inverter will never work. If it is more, it will never work. So all the inverters has what you call operating window. Okay, this is if you don't have a DC-DC converter in between. But if you have a DC-DC converter, so there are two objectives. One is to achieve maximum power and also regulate the DC. Because, for example, the voltage drops below 150. So maybe if we are using a boost converter, we can boost up the voltage. Or if we are using a buck boost, so we can boost and then we can also step down the voltage if needed. You got what I mean? So this additional hardware has a dual objectives, which is to track the MPPT and also maintain the voltage on the DC bus. Is that answers your question?
Yeah, got it, sir. Got it.
Any other questions before we move on the MPPT? By the way, actually, if you look into the current research, is now we have moved from MPPT to FPPT. Anyone knows what is FPPT? FPPT means flexible power point tracking. What does mean flexible? I think yesterday I mentioned something about Australia, where in sometimes we achieve more power from the PV panels than what we need. So how are we going to control this scenario? One of the way to control this scenario is to use the FPPT. MPPT is always pushing the PV panel to operate at the maximum power, right? But if I have a scenario like this, for example, we have a lot of power from the photovoltaics, how I'm going to control it? If I have a flexible MPPT or FPPT, I can say, okay, all it have to operate at 50%. So the power will cut up to 50%. So like this, I can control the injected power to the grid. Is it clear? Because But also this FPPT will also operate at the MPPT or look for the MPPT in case we have need more power. So that's why I say that there is a need now. This is not only as to extract the maximum power, but also you need to deal with the situations where you have extra power and you don't know what to do with it. Either you disconnect or you can operate at 50%. So instead of disconnecting, okay, we can say, okay, we send the control signals to all these MPPTs to operate at a 50%, of their power. So they can block the amount of power, only 50% goes. And that's actually the importance of having the FPPT now. Because MPPT now, still in use, okay? And these are some examples of hardware, These are some examples, actually, like I said before. It's a DC, you can see here, 2 terminals, output and input, okay? So it's all, sometimes it comes built in within inverter also can be the case. And this is how the control structure of the PV system looks like, okay? Maybe I think we have how much time? We have now 1 hour. Maybe we have open for questions. Maybe you can stop here for a while. Maybe we take any questions from the participants on this second part before we move to the next one, which is the control of the PV inverters. Is there any questions from the audience?
Sir, I have one question.
Yes, please.
During the flexible power transfer, is it, the grid is there and the battery is there, right? Then we can also be able to track that MPPT, right? Instead of going for 50%.
I didn't hear you. In the FPPT?
Yeah, instead of going for 50% of the maximum power, we can go for MPPT and deliver the extra power to the grid or the storage system, right?
Yeah. I'm talking about the case where we have, for example, I say we have reached to here in Australia, in sometimes 100% from a rooftop. 100% electricity is produced only from the rooftop. So forget about the large power plant, cool power plant, gas power plant, which running. So we have a lot of extra power. So in this case, if you have storage, the ideal case is to store this power in the grid, in storage. But if we have too much to be stored, so if we let this system continue, it will collapse the grid. So the best is to operate these rooftops at 50%. So we reduce the power that is available on the system. Okay, so that's why we need the FPPT. So that's the idea, But if we have storage, yes, that is ideal actually. To have extra power, then we can dump it. But do you have the capacity or the storage availability that can hold this amount of power at this point of time, Okay.
Now, what actually I thought was there is some an ideal loads where you are going to dissipate that to that particular load. Maybe this is I didn't got it this kind of an idea at any time.
Yeah. I think that's why yesterday what I mentioned. When we have this kind of thing, that's why now there is a lot of investment in green hydrogen, production. So when you have this extra power, actually you can activate your electrolyzers to produce the hydrogen because you have extra power which you don't need. So you can make use of this power to generate hydrogen. You have a pumped hydro. So this is the time to activate your pumps to pump back the water back to the upper reservoirs. Okay. So these are the avenues which there are megawatt level battery storage systems, here in Victoria where they can store this amount of power. So these are the initiatives or some of the ideas actually where we can make use of this extra power instead of blocking it, because some people doesn't like to block it, So because they invest a lot of money, so they want to sell or they want to use this power. If they want to use, there should be no problem. But using it, that's another challenge. So these are some of the areas which we need to look at. Okay. Any other questions? Okay. If there is no questions, then we can move to the next one. Maybe I have to share again. Okay, share entire screen, screen number 2, share. Okay, and then full screen. And then okay, and then
It's now okay, Professor.
Sorry?
It is okay. You can go ahead.
Okay, yeah. So maybe this one we come to it later, the control of the vessel. So let's look into the loads. Okay, this is just a small example, okay, for this session. So this is some of the electric loads. So for example, when we want to calculate the load, So electric loads can be either AC or DC, the utilizations for in microgrids. We will have a combination of both. DC load typically operate from batteries, okay? AC loads usually powered by inverters or generators or utility or grid, okay? So this is the terms, the energy we use, the power and the time. So these are also very important. I think this one was quite good. Most of these what you call PV systems will have what you call remote monitoring options, okay? Because these microgrids, sometimes they're installed very far away. So they come out with some remote monitoring systems. So you can remotely monitor the conditions of the system. Okay. So and this is also very important for research, because we want to extract this data and later on use this data for research purpose. For example, this some PC interface, because Trace. This is actually it's a company which provides this software, so we can monitor actually the power generation. This is very important in microgrids. So how much from the grid that comes from the grid, how much that injected to the grid, how much is going to the load. So for example, here we have a 3.3 kilowatt. So we have 1.1 we inject to the grid, and 2.2 is injected to the home is the load. Let's say see the total consumptions. So self-consumption rate is 66%. So we have another what you call 34%, which is injected as a feed-in. Right? So, but this scenario keep changing. So this has a good feed-in between 12 to, for example, 4 p.m. in the afternoon. But once it gets cloudy, whatever, so the scenario is totally different. And this is the forecast. Okay. All right. So this is also another interface. Usually this is a Sunny Boy. We have this system in our lab. We have this monitoring system in our lab. So we use this Sunny Boy. And this actually gives you also the same. So the power, how the power looks like, and it give you even the location where you are, what is the, what you call the current power, what is the inverter consumption, comparison status, the energy, and give you all the detail, and then how much the saving that you save, and also the weather, So it's actually a very useful interface that can be used. Okay, so I think we talked about this before, but there are two types of either is standalone or it is grid connected, or we call it interactive systems. Okay, so these are the two types of PV systems. So if we look into the direct couple, we call them direct coupled PV systems. So what we have the PV array, DC-DC converter and the load. So here, there are a few conditions for this system or for this direct couple to work. First one, it must be a DC load. It cannot be an AC load. And also, there is no need for energy storage. Means we don't need energy storage in this. It's directly coupled. And the load operates only when there is sun. I think you got what I mean. I think is this clear? So maybe I can give you some application of this. For example, water pumping. Water pumping, actually, this can be useful. You know, for example, if you, for example, you use it for irrigation, doesn't matter when. Actually, during the day, maybe you need 4 or 5 hours, so we can directly connect, you know, to the load. You don't need any other storage because the system is very cheap. Okay, but the load here need to match the source. You know, means there are some applications where we need this. Some ventilations, for example, where this ventilation is required only during the day, so we can use these kind of systems. Okay, most of this load must be well defined, okay, and operate daily and not subject to user control. So there's no control. Means it self-regulates itself, and uses charge controllers. Okay, but in this case, what we have here, we have a battery in the middle. You know? So the battery in the middle here. So the PV charge the battery, and then the battery supplies the load. Okay. So the previous system we have no battery. Now we have standalone with the charge controllers and with the battery, so it charges. But also this one can be like this, where we have a charge controller in the middle. So we have a PV battery, charge controllers, and then battery, and then a DC loads. So here a charge controller is required in most PV using the battery systems. So there are different combinations. Okay, so we can charge the PV with the battery directly, but it will not be optimum. We can have this combination, standalone PV systems with the charger. So we have a charge controllers, and we have battery, and then we supply the load. Okay, so this is the another configurations. Also, we can have standalone with the charge and the load. So we can have the PV systems, charge controllers, load controllers, and then we have another load here. Okay. This is to protect from overcharging of this battery, so we can discharge it from the battery to the load. Standalone PV systems with the multiple chargers, so we can have a few subsystems, subsystem 1, subsystem 2, subsystem 3, and so on, and they have charge controllers, and then we have the battery, and then we have the DC load or the inverter. Also, we can have even the inverter here to convert the power. Okay. Standalone, okay, also with the charge controllers, battery, and then diversion controllers, and then we have the load. So this is also another configuration, because they are quite a number of actually configurations. And then we come to the last one, standalone PV with the what you call AC loads. For example, here AC load, then we need to have the inverters inside. So PV array, charge controllers. We have a DC load, and then we have a battery, which can also use, and then we have AC load, which is supplied from the inverters. And also we can even use the AC source to charge the battery here, because this has to be bi-directional. Okay? So this is a standalone. Also, we have a hybrid system, okay, where one is DC, okay, another one is AC. Okay, and they can have in between a storage system. Okay, so PV to charge controllers, to the load, or to the charge. Here we have, for example, an engine or diesel generators or wind turbine, and then we have the inverters, and maybe charge controllers, and then we have the load, the AC loads. So this is called hybrid systems. Also, we have what you call grid connected systems, when we have a PV and then inverter, we have AC loads, okay, and then we have the electric utility or electric grid. So this is you can see here we do need storage. Why? Because we have the grid. Means in case we have extra power, we can sell to the grid. If we need power, we can buy from the grid. Yeah, storage can be added, okay, but we need to do the techno-economic analysis of the systems to see is it feasible or not. Okay, either to have a storage systems depends on the price of the feed-in tariff and other cost of the systems. Also, we have this where also is grid connected, but you can see the utility is not going directly to the battery. You know, it's not in between, because the previous one you can see here is the battery is in between here, but here you can see we have a PV array, and then we have the charge controller that charge the batteries, and then we have an inverter here, and then we have either goes to the load or goes to the grid. Okay, and also you can also supply some backup for critical loads in case there is a critical load. But also we can bypass this. For example, from the PV panels, you can bypass this part directly to the load, because, for example, you have an AC supply, you know, AC from the utility, then it goes this way, and then we can bypass this in case this something or some faults happens, whatever, you know. Okay, good. So maybe I think we have another 10 to 15 minutes. Maybe we give an example, okay, and then or maybe I don't know, it's 20. Maybe we give this example. It's just an example actually of a hybrid PV battery system design. Okay, so in these systems we want to design a hybrid PV battery, small microgrids. Assume that we have 500-watt light bulbs, and they've been used for 2 hours a day. And this is a small home. And then we have 3 fans. Each fan is 120 watts and operate maybe 3 hours a day. Okay, so this is just a small home. Then we calculate, for example, we said 5 times 2 times 100. So it's around 1,000 watt-hour per day of energy consumption. These 3 fans, which operate for 3 hours, which consumes around 1,080 watt of energy. So the total is around 2,080 watt-hour per day. So that's the total energy consumption per day. Or we can see 2.08 kilowatt-hour per day. Okay, so now if we want to do the now we know the load, because now we have estimated the size of the load. So let's see the source now. PV panels. So we want to have a PV and battery, like we said before. We have 2 choices. Okay, so like I say, we have quite a number of losses. We have the loss factor, because of PV panel produce 100%, it will be able to supply only 70% losses. I remember before. So here is we multiply by 1.3. So 1.3, that's when we add it to the load. So once we multiply by 1.3, so the load actually becomes 2,704 watt-hour per day. Okay, so this is what we call the losses inside the system. So they are 30% losses. Okay, if we assume that actually 100% that comes from them. So let's, for example, we look into there are different PV modules. Okay, variable. Some of them, for example, this is a 250 watt peak, 24 open circuit voltage, and 8.55 amperes short circuit current. Okay, this is the rating. This is the so if we have 6 of them, so 6, for example, individual panels, it's equal to the rated power times the number of sunshine. For example, if we assume the sun hours, because in every locations there is the sun hours. This is not the sunlight. I think that's very, very important. And if you look into here, anyone knows the difference between sun hours and sunlight? Anyone? Maybe we have to come to this one. Yep. Anyone knows what is the difference between the sun hours? Because in the PV systems, we use the sun hours. We don't use the sunlight. For example, you may have sunlight which start from 7 to 6, but the sun hours is only 6 hours. Maybe it's from 9 or 9 o'clock to maybe 4 p.m. only. So this is called sun hours. Okay, and this sun hours changes in winter and summer. In summer, we will have longer more sun hours. Okay, but in winter, the sun hours becomes late. Yeah, they are related to the sunlight, but it's different. So the main difference is sun hours means there is enough energy from the sun to produce power from the PV panels. Because if the power is too low, that will not be able to turn on the inverter or charge the battery, whatever. It's the power. Yes, there is a sun, but it's too low. So it's not sufficient. That's why we always use what you call sun hours. We don't use sunlight. Okay, and most of the time, the sun, what you call. Where is it? The sunlight, okay, usually it's maybe a half of the sun hours is half of the sunlight. For example, you have 12 hours, maybe the most useful, maybe there are 6. Most of the country can go up to 6, 7, very rare to find 7 and 8 sun hours. Is that clear? For example, this I take this Kuala Lumpur, in Malaysia. So usually Malaysia is a tropical country, so they have 12 hours sunlight, 12 hours a day, night. So it's near to the equator. So out of 12, there are only 6 sun hours. I don't know in India, maybe you need to know this because this is very important, because that's to give you the amount of power. So if you have 250 watt panels, so how much power it's produced per day? It's 1,500 watt hour per day. Okay. So if you want to know the number of panels that we need, what is the total number of panels required? So the total number is 2,700, which is the load plus the losses. Remember, 2,700 divided by 1,500, which is the watt hour that is produced by one panel. So we get 1.8. So actually, it's approximately 2 panels. All right. I hope it's everything clear so far. Okay. And then,
Professor?
Yes.
Yeah, it is time now, 10 over here.
Sorry?
It is time, it's 1.5 hours is over.
Yes. So maybe we
take
can
some questions and then we'll stop. And then
maybe we can have 1 or 2 questions before we start. Any question? Any
in chat box there are questions are there, Professor?
Can we use on-grid inverters as datacom or DVR? night time, because they are not. Yeah, that's good equations. Yeah, it's so far it's not been used in real life, in the real systems. It's not been used, but that's a good, actually, a good topic to investigate and to look at. Yeah, because most of the time they are not used at night. Yes, that's true. So we can find, but in practical, it's not yet used. Okay, it's not, but it's a good, interesting, actually, idea to look at. How to use this kind of inverters. There are quite a large number of them, especially at night. All of them are ideal. They are not being used. Yeah, that's good. Another one, Sheikh. I believe data-driven analysis help use better to size the panel and battery. Yes, very, very true. Yeah, very true. Data analytics, if you have a lot of data from both load data and also source data. When I see source data, I'm talking about, for example, the wind speed, the irradiance, the temperature, and also the load profile data. The more data you have, the more you can accurately design your PV panel systems. Yes, very important, because when we see just now 2 hours, 3 hours, this is approximate. But if I have a load profile for 1 year, okay, or 2 years or 3 years, then I can accurately actually calculate or predict my load. Okay, yes, very true. There is another one. This is Veltec, okay, Chennai. There are so many types of MPPT in research. Even people talk mini swarm optimization through hybrid-based optimizations. But why still few all MPPTs are popular? Why still few all MPPTs are popular? What are the difficulties in implementing? Why many research are only on papers? Very true. I agree with you. Like I mentioned just now, the one used by industry is still the P&O. Okay, why? Because it's simple. Because industry doesn't need a complicated one. You need something very simple, functional, reliable. That's it. Very straightforward, and do the job. So what actually the large number of MPPTs that exist in the research, which is end up in the papers, like you mentioned, these are like some of them require very high computational time, very, very complicated, still not proven yet to work or not. So mainly most of them are tested on the lab scales, and most of these MPPT are tested on solar simulators, not on the actual PV systems. That's why they end up only in papers, because if you want to deploy it to the industry, you need to test it on the actual PV systems and how. For example, during partial shading conditions. I forgot to mention about partial shading, which is also a very important topics. So that's why most of the industries prefer the conventional P&O incremental conductance methods. Yeah, very true. Thank you. Any other questions? All right. If there is no questions, so see you in half an hour time.
Yeah.
Right, Dr. Siva?
Yes, Professor.
Okay. Sir, thank you, sir. I still recall my few occasions I had with you when you are here. Veltec, yes. It was a pleasure to meet you too. Hopefully we